For this question, first of all, we can say that the distribution is B 16 0.3. Now what does that mean? Well, if we write the general binomial distribution, it's BNP, and N is the number of trials or number of events, and P is the probability of success in each event. So in this case we can see that N is equal to 16 and P is equal to 0.3. Now in this question it says you have to show your calculation. So although you can do this on your calculator, and that's not a bad idea for checking your answer, you do need to write out the full calculation. Now if you've done enough practice, you probably will have learned what the formula you need is, but it is included in the formula book, so you could look that up if you can't remember, or to check. So here it is, and so we have that the probability that x, the distribution, is equal to x, meaning that we get this number of successes, is ncx p to the power of x 1 minus p to the n minus x. So in this question we want p of x being 7, so we can put our numbers in, and we have 16 for n, 7 for x, p is 0.3, so that's to the power of 7, and then 1 minus 0.3 is 0.7, and n minus x, which is 16 minus 7, is 9. And then we pop that in our calculator, and you're not expected to work that out by hand, and we get 0.10096 and so on. It's not specified as to how many decimal places we need to write, but given that the tables give 4 decimal places, then we'll round it off to 0.1010, and we'll put 4dp just in case they want to know what we've done. As I mentioned, you can check your answer using your calculator. It's also worth having a feel for what the answer should look like. So this is a Geogebra app. This one's online. If you go to Geogebra website and then put binomial distribution in as a search, you'll find lots of possible ones to have a look at. So we want to set n as 16 and we want to set p as 0.3. And for a probability distribution, we know that the total area of these will be 1 because it's certain that one of them will happen. And we can see our bar for probability being 7 is here. But obviously you can't use this in an exam, but you can have a play with it outside of when you're studying. And we can see it has this sort of bell-shaped curve to it. That changes a bit if we make the probability more extreme. So this is skewed and there's a long tail. And of course if we go the other way we see the other thing happening. So we put it in the middle, probability of a half, so this would be a fair coin for example. And we can see the shape doesn't really change. Now if we put it to an extreme, we can see that we still get that pattern of skewing. Now you'll see on the left hand side here, that's the formula for calculating a binomial probability. On the right hand side, which is a clip also taken from the formula booklet, you'll see a formula for the coefficients of a binomial distribution. And this comes from the binomial distribution a plus b to the power of n. And you may well have looked at the similarities or connection between the binomial distribution and the binomial series. But it's worth being clear on that. It helps you to understand both. So we'll just have a little look at that. First of all, although the two formulae that come from the formula booklet look similar, they're not quite the same. What we can do, though, is that we can change r to x, because the r is arbitrary to show what the coefficient is for various different values of r, and so that would give us ncx a to the n minus x p to the x. We could also then say that b is equal to p, probability, and a is equal to 1 minus p, and that gives us ncx 1 minus p to the n minus x and p to the x. And then finally, and you're possibly getting a little bored by now, but we could swap those round. That's a nice easy move. It's worth pointing out here as well that because if you do any wider reading, that we often use q to equal 1 minus p, in which case both of these formulae would turn into ncx p to the x q to the n minus x. Now, to think about the connection between the distribution and the series and why it happens, we've seen that the coefficients from the binomial series are the same as the probabilities from the binomial distribution. But why? Why is that? Well, let's think about the situation we've been dealing with. We have a probability of success, p, and a probability of failure, q. And between them, they add up to a probability of 1, which is certainty. So we are certain to either fail or succeed. It could be some other pair of things. It could be red and blue counters. It could be heads and tails, whatever. Doesn't really matter. So if we were to, let's call it heads and tails because it's familiar. So if we say p is the probability of heads and q is the probability of tails, and we don't know if it's a fair coin, so they may or may not be the same. So how would we write a head followed by a head? Well, we could write it as a head followed by a head, and we could also get a head followed by a tail. We could get a tail followed by a head, and we could get a tail followed by a tail. Notice here that pp means p times p, and that means the probability of two heads. And we can just multiply them because they are independent events. The probability of getting a head the first time doesn't affect the probability of getting a head the second time. And this is, of course, one of the conditions for a distribution being a binomial one. Now, the binomial distribution comes from multiplying brackets. So if we had p plus q times p plus q, we would normally write that as p squared plus pq, two of them, plus q squared. But we don't have to. We could write it as P times P plus P times Q plus Q times P plus Q times Q. And we can extend that further. If we had 3 trials, then we could have head, head, head. We could have head, head, tail. We could have head, tail, head, and head, tail, tail. Tail, head, head, tail, head, tail, oops, and tail, tail, head, tail, tail, tail. And then we could group them, so the ones that have 3 heads, P, 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 then the ones that have 2 heads, P, P, Q, P, Q, P, Q, P, P, the ones that have 1 head, P, Q, 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 P, Q, 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 P, and the one that has no heads, which is the same as 3 tails. And these are exactly the same terms as we would get if we were to multiply P plus Q by P plus Q by P plus Q, which is the same as P plus Q cubed. When we've written all those 8 possibilities down in this row, then the order that things have happened in are different. But we don't care about the order when we're trying to find out how many heads we got when we tossed 3 coins. And so we can bunch these ones and these ones together, and we can say we've got 3 heads and there's only 1 of them. We've got 2 heads and a tail, and we've got 3 of them. We've got a head and 2 tails, and again there are 3 of them, and we've got 3 tails and there's 1 of them. And so we get the familiar 1, 3, 3, 1, which is what we would get if we, in the usual way, were expanding P plus Q cubed in a non-probability situation. So we would say we have P cubed plus 3P squared Q plus 3P Q squared plus Q cubed. Many of you will recognise the 1, 3, 3, 1 from Pascal's triangle and know that this gives us the coefficients of expanding brackets. It's worth, just as an aside, thinking about the naming of things. We call it Pascal's Triangle after Blaise Pascal, who was a mathematician, and he was and a philosopher for that matter, and he was very interested in gambling. And of course, probability connects very closely to gambling. But he wasn't the first person to come across or discover or invent the triangle that we give his name to. In fact, it was known in the BCE era, and this picture is from India in the 8th century, and this picture is from China in the early 14th century. Pascal was working in the 17th century. Anyway, going back to his triangle, we probably know the lines above, and we know that we can make the next line by adding the two numbers above. So that line we've just drawn allows us to say that a plus b to the power of 4 will be a to the power of 4 plus 4 a cubed b plus 6 a squared b squared plus 4 ab squared plus ab cubed plus b to the power of 4. I don't know if you've ever wondered why it is that we can get the next line by adding the two numbers above, but it's a nice little thing to look at. So if we think of going from the squared line to the cubed line, we have a plus b squared equals a squared plus 2ab plus b squared. So that's that line. Now, if we want to turn that into a plus b cubed, or if we want to work out what a plus b cubed is, then we can do a plus b times a plus b squared will give us a plus b cubed. So we can I'm using colours, I'm not going mad, I'm using them for a reason. If we replace the a plus b squared by the expansion we already did here, then we have a squared plus 2ab plus b squared. And then if we multiply that by a, we get a cubed, we get 2a squared b, and we get ab squared. If we multiply it by b, we get a squared b plus 2ab squared plus b cubed. Now, if we put our original a plus b squared onto its line, if we now, going in this diagonal, multiply each bit by a, then we get a cubed, and then we get 2a squared b, and then we get b cubed, and then we don't. And then we get a b squared, and those are of course the same as what we had here. And then if we go down the triangle the other way, we get a squared b, we get 2ab squared, and we get b cubed, which of course are the ones from there. And so we see that if we want to find the number on the next line, we can sort of see this lovely triangle here that takes everything in. And we get our final answer here, so we get a cubed plus 3a squared b plus 3ab squared plus b cubed. And I'll leave you with a lovely poster of Pascal's triangle showing you various properties, which those of you who fancy it could have a go at proving using, if you like, the binomial coefficients. There you are.